Good evening, everybody. So, in this lecture, we will discuss on the topic impulse momentum principle and its applications. We have learned about one of the basic principles of fluid mechanics, that is, the continuity equation in fluid kinematics. Then, another principle, the Bernoulli's equation or energy equation, is learned in fluid dynamics, and its applications also we have discussed. Apart from these two, the continuity equation and the Bernoulli's equation, one more important basic principles of fluid mechanics, which is very important to solve the fluid flow problems, that is the impulse momentum principle. Now we are taking it. This impulse momentum principle is based on the conservation of momentum. What the conservation of momentum states, the net force acting on a fluid mass is equal to change of momentum of the flow per second. Right? This is the conservation of momentum. Based on this conservation of momentum, now we express what is impulse momentum principle and what are its applications. So once again, I mentioned that in fluid kinematics, we have learned one equation called as the continuity equation. This is the one of the basic principles of fluid mechanics, which we generally, in what form we have used that equation is Q is equal to A1 V1 is equal to A2 V2. So the relationship between discharge, velocities and areas we have established using this equation. The second equation which we have learned is the Bernoulli's equation. And Bernoulli's equation is the energy equation. This is actually to establish the relationships between pressure and velocity between two sections, P1 by gamma plus V1 squared by 2g plus Z1 is equal to P2 by gamma plus V2 squared by 2g plus Z2. This is for non-viscous fluids. And if you want to use the same equation for real fluids, then only thing is the head loss comes into picture. P1 by gamma plus V1 squared by 2g plus Z1 is equal to P2 by gamma plus V2 squared by 2g plus Z2 plus head loss. This is what we have learned. So the first equation establishes the relation between discharge velocity and areas. The second equation actually establishes relation between pressure and velocities. So these are the two equations. Now the third equation that which we are proposing is the impulse momentum principle. This is what the focus in this lecture is. The impulse momentum principle or impulse momentum equation. Anything. The impulse momentum equation. So the impulse momentum equation is based on basically the conservation of momentum. This is the basis for us for the impulse momentum principle. Conservation of momentum. What conservation of momentum states that the net force acting on a fluid mass, right, is equal to change in momentum of flow per second, right? You take the direction, any direction, net force acting on the fluid in any direction, and here also same direction, right? Now if I take it, what is the force acting on a fluid mass? Now if I take it, force acting on a fluid mass, and mass I will take it as m, mass m is given by which law actually? It is given by Newton's second law of motion. What Newton's second law of motion states, force is equal to mass into acceleration. What can I write for acceleration? Acceleration is equal to dv by dt I can write. So therefore F mass into dv by dt. As mass is constant, I can take it inside derivative also. It is d by dt of mp. So now if I bring F into dt is equal to d of mv. So this is what exactly the impulse momentum equation is. What it states, this F dt is nothing but actually the force acting for a short interval of time, for a short interval of time. And this is what we call it as impulse. Then what is d of mv? D of mv is nothing. Mv is nothing but the momentum. D of mv it will change of momentum. So that means impulse is equal to change of momentum. This is what exactly basically the impulse momentum principle means. But remember that both the things actually we need to take in the same direction. That is the one of the important thing. Where we apply this impulse momentum uh, principle or impulse momentum equation. Number one, basically, wherever there is an abrupt change of velocity in magnitude or direction. This principle is very much useful for flow analysis. You can ask me where such type of things will come, for example. So wherever abrupt change means, for example, sudden enlargement of pipe, sudden enlargement of pipes, or hydraulic jump in open channels. This is number one. Number two is especially jet propulsion and propellers. And most important thing is in all hydraulic machines, all three equations are used: continuity equation, Bernoulli's equation, and this especially in turbines, jets. Then, but at this level, you have in your syllabus only one application, that is pipe bend. This is the only application we have at this level. What this pipe bend, what we are going to use it? Because of the pipe bend, actually, the bend position, naturally some external forces are exerted on the fluid, right? and the fluid exerts an external force on the bend. So to determine those forces, to determine the force exerted, the force exerted by the flowing fluid on a pipe bend. So this principle is used, and in your syllabus, they have mentioned clearly how to solve the pipe bend problems. That's what they have given in your thing also. So that straight away I will take it. The other three, actually, if you go for a study of open channels, the first application will come. Then in the case of pipes, the minor losses, if you study, then naturally sudden enlargement of pipe will come. Then if you suppose you go for propulsion studies, we will get the second. And if you go for hydraulic machines study, then we get the third application. But what we have in our syllabus is only this now. So now if I take pipe bend, how the pipe bend looks like. For example, if I take it, suppose this is the pipe bend. Here the pipe is bending. So now this is the pipe. So pipe we have bent it, and right. Suppose this is the first section, and this is the second section. If I take it, this is the direction here, and now the flow takes place here like this. This is how it flows. So in such a problem, so what is the problem actually? Here it is. Now if you take it, this the flowing fluid which is flowing in the pipeline applies force on the bend actually. This is Fx and this is Fy. So this is the force which we have to calculate. Force exerted by the fluid on the bend. What is that force? That we have to find out, and that is what we call it as the basically the force on the pipe bend, which is solved by using this impulse momentum equation actually. So now in order to solve the problem, to determine the resultant force, the resultant force exerted by a flowing fluid on a pipe bend. This is our problem. Now I have taken already two sections as explained actually. Suppose if you take it, consider two sections, 1 and 2, right? Let V1 is the velocity at section 1, V2 is the velocity at section 2, velocity at section 1, velocity at section 2. P1 is the pressure at section 1. P2 is the pressure at section 2, right? Then A1 is the area of flow at section 1, area at section 1, and A2 is the area at section 2, right? Now Fx and Fy are the forces exerted by the fluid on the bend. Therefore, what is the force? What are the forces exerted by the bend on the fluid? Naturally, it will be minus Fx minus Fy in x and y directions. Right? Now knowing this, now we will take it actually. So apart from this, what you call it as force on the bend, the other forces is only the pressure forces. There are only two. There are two forces, right, acting on the fluid. Right. Number one is the pressure force. Pressure forces at section 1 and section 2, and second one is force exerted by the bend, F minus Fx minus Fy. These are the two forces. Now if I apply the impulse momentum equation in, so now what is the uh, applying applying impulse momentum equation, impulse momentum equation in x direction, net force acting on the fluid, acting on the fluid in x direction is equal to rate of change of momentum in x direction, or change of momentum per second in x direction. Now if I take actually at section 1 and 2, now what is the figure again? Once again I recollect, once again I will draw and show. So this is the thing. So this is first section and this is the second section. So what are the forces here? This is pressure force here. The force acting on the fluid. The in the all here is what, for example, this is if I take it. So this is all fluid. Right? This is the pressure force P1. So next actually this is an equilibrium because of the pressure force P2 here. Right? So now pressure force P1 direction is, this is the direction of P1. What is the direction of P2? This is the direction of P2. So if that is the direction of P2, naturally what is the direction here, and this is the direction. So if P1 is the pressure, what is the area? P1A1. So force P1A1 is acting in x direction, whereas force P2A2 is acting in the inclined direction. If its components, if I take it in x direction, it is P2A2 cos theta, and in y direction it is P2A2 sin theta. This is first. Pressure is over. Now what is the other things? And actually when I am calculating the similarly what I mentioned, actually the force exerted here on the bend is, we mentioned it as Fx, and similarly on that side y. So what is the force applied by the bend on this? The force applied by the bend on the fluid is what? It is minus Fx in x direction. So this is pressure force. This is the force exerted by the bend on the fluid. So these are the forces. Two forces have come. Then what is the next one? The velocity. So the velocity components, if I take in the x direction at section 1, it is directly v1. So v1 is the velocity at section 1. What is v2? This is how v2 is. That means actually v1 is acting in this direction. How v2 is acting? V2 is acting like this. So then V2 is acting, then what is the component if this is theta? V2 cos theta is in x direction and V2 sin theta is in y direction, right? So pressure diagram is first once again, this is how the pressure forces are. Pressure forces, if you take it, this is P2 A2 cos theta theta, and this is P2 A2 sine theta. This is regarding pressure. Whereas the velocities, if you take it, this is how the velocity is v2. So it is in this direction v2 cos theta, it is theta, and in this direction v2 sine theta. So knowing this, now let us straight away apply the Bernoulli's the momentum equation. Right? The equation, if I write it, is pressure net force acting on the fluid acting on the fluid in x direction. First is that for me. What is the first force at section 1? It is P1 A1. What is the pressure force at section 2? Minus P2 A2 cos theta. This we are taking it in the x direction. This we have taken in the x direction. What is the other force apart from that at which we are having? The force due to the bend. So this is the force, net force acting on it. And next, what is the other one which we have to find out? What is the change in momentum per second? Change in momentum per second in x direction. So if I take it, change in momentum per second is equal to, it is the mass per second into change in mass into velocity. That means final velocity in x direction minus initial velocity in x direction. So mass means actually if q is the discharge, rho q is nothing but mass flowing per second. What is the final velocity? Final velocity is v2 cos theta minus initial velocity is v1, right? So this is one equating the above, equating the above. If I equate it, it is P1 A1 minus P2 A2 cos theta minus Fx is equal to rho Q. Rho Q is nothing but mass flowing per second. Final velocity V2 cos theta minus V1. So this equation, using this, you can find Fx. This is first. Similarly, if you apply same thing in the y direction, applying applying impulse momentum equation, impulse momentum equation in y direction, right? Again, what we have to write it, it is a net force acting on the fluid, acting on the fluid in y direction, in y direction is equal to change in velocity, change in momentum, sorry, change in momentum per second in y direction. So now I will find out What is the net force acting on the fluid in the y direction? So at the initial stage, the whole pressure is only in the x direction. So what is the net pressure, initial pressure in the y direction? It is 0. 0 minus P2A2 sine theta. Why 0 is because the entire pressure is in which direction? The entire pressure is only in the horizontal direction. There is no pressure component at the section 1 in y direction. That is what which we are. And then second, the pressure at the second section is already it is acting in the inclined direction. So the components we have taken. Whereas the third one is the force by the bend on the fluid. The force by the fluid on the bend is in the upward direction. Therefore, force by the bend on the basically fluid is in the opposite direction. So it is this is equal to mass flowing per second into final velocity in y direction minus initial velocity in y direction. Mass per second is nothing but rho q. Final velocity is it is v2 sine theta minus initial velocity in the y direction is 0 because the entire velocity at section 1 is only in the horizontal direction. So this 0 and this 0 because the entire pressure is in the horizontal direction at section 1, and similarly entire velocity at section 1 is a horizontal direction. So the vertical component. So using this equation we can find what is Fy. So this is how the forces a force exerted by the fluid on the bend, which we can find out using this. Once Fx and Fy are found out, then you can find out F is equal to square root of Fx square plus Fy square. This is next. And the resultant angle made by the resultant, angle made by the resultant force with horizontal is equal to with horizontal. That means is given by tan phi is equal to, if I write, it is f phi by fx. Using this equation, you can find out what is the result. So if you find out this problem, this topic is over. Now we will take up actually the problem on this topic, which is more prominent, and definitely you can expect a problem on this particular application of impulse momentum equation for a pipe bend. That generally most of the cases we get a pipe bend problems in this topic actually. So we will solve a problem in the immediate class on the application of the impulse momentum principle to determine the force exerted by the fluid on a pipe bend. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.